So now, mathematically, just in a simple way, if you have an inertial particle or an inertial frame, and it's in a warped space-time, it's actually a free-fall frame, and you'll take some kind of coordinates and you'll say that this is equal to 0. Okay, my acceleration is 0, and these are good, valid coordinates. Taking the equivalence principle along some given geodesic and saying you have this free fall particle, we know that that's the inertial particle, that's the geodesic, and therefore I'm going to write this straight line equation, even though ordinarily, naively, Newtonally, I would never have written this equation. I would have written that this is equal to minus gm over r squared. The ordinary Newtonian, you would say you have a particle, it's falling, it's accelerating. You have the second derivative of x with respect to t is minus gm over r squared.
Yes.
Right? But because of the equivalence principle, I'm going to say that it's 0. This is a geodesic equation. If you take seriously the fact, and you agree that one can see this free-falling particle's world line as a geodesic,
yes,
right, then, it's a straight line. So I write the straight line equation. This is what Mr. Wheeler does. He doesn't talk about warping time. He talks about just how you define time.
Sure.
Right?
Sure.
But I'm just using that calculation. Now I'm going to transform to a different frame in which I have a poor definition of time. This is the warped time, which is the true perspective, and I'm going into now comparing it to a frame in which I'm using the time that we naively use in Newtonian physics, which is not warped. We're not taking into account the warp. So where this time is a function of this time, right? It's some function. In other words, basically, it's a stretch. It's the one-dimensional parameter change. Okay. So it's this plus this equals 0. Which means that this equals to this when there are minus signs and so on. So basically, I now have a new phenomena using the x coordinate and my bad time, so to speak, right? You'll see that this is equal to minus this over this. So you have an acceleration given by this. All right? So that's the bottom line. The conclusion is that you will notice if you're using an axis system, using this bad choice of time, right, you're going to claim that you're going to see this.
Yeah.
So you see an acceleration, and this is the amount. Again, if you're just having a one-dimensional line, you can reparametrize O's. But if you have this space axis here, so that you have a relative scale between them, that's the thing that allows you to actually define this in a way which can't be reparametrized. If there really is this time warping,
yes,
and what I'm saying is that really it's the free fall frame which has this equation true,
yeah,
all right? If I'm going to be using a non-free fall frame, like this supposedly, allegedly Newtonian inertial frame of a stationary person, right? You're going to end up, and if you're saying that the difference between them is a transformation of the time, then this is how the acceleration would arise as a result of that, in a schematic way. Of course, one has to define carefully a space-time and what does it mean to warp space-time and so on, but this is the phenomena, this is how the phenomena would look in a kind of like a heuristic sense. This is really the geodesic equation, and that if you stick in that this is just t, you get the same thing, you get exactly this.
right.
This is from Weinberg. he does a very nice calculation here.
Right.
Does this? This
Right.
is the second derivative equal to 0.
Right.
It's very similar. He's doing it, of course, for a covariant system where you're transforming space and time.
Right.
I'm doing it specifically for time only.
Okay.
Right?
Sure.
But basically, when you do this, you end up getting the geodesic equation.
Of course. Yeah.
Right? And if you do it, here I just wrote the psi going to x of Mismethorn and Wheeler.
That is Minkowski's where
Right.
space can transform
Right.
by some coordinate system.
Right. So if you defines what the Christoffel symbols are based on this transformation,
Okay.
so you can see that it's an acceleration basically.
Okay.
And he then shows you if you're transforming the Euclidean, well, the Minkowski metric,
Yeah.
you end up with some transformation that he defines as the metric
Of course.
coefficients, right?